So now let's talk about the discovery of things that now we know are found in the atom. So currently we know that the atom, which is the smallest particle of any element, contains what we call subatomic particles. Currently we know that the subatomic particles would include electrons. They include electrons. We have protons, and the last ones to be discovered by experiments were neutrons. So there are experiments that brought about the discovery of electrons, protons, and neutrons, and one of them is cathode ray tube, or what people would call the Thompson experiment. Okay, so this is the Thompson experiment. Now, just to go ahead of us, the Thompson experiment was the first experiment to give evidence of electron existence. This was the first experiment to say the atom of any element has electrons in it. Thompson was the first person actually to tell us about the existence of an electron and give us an idea of its charge. What you're looking at here is cathode ray tube. So what did Thompson do? He took a piece of a cathode ray tube. Now it's called a cathode ray tube because the ray created in there was a cathode ray. And this cathode tube is coated. It's going to be coated with, I believe it was zinc sulfide, which glows. So it's a fluorescent chemical. Let's just say the tube was coated with a fluorescent chemical. That fluorescent chemical would glow, or after the experiment or during the experiment was seen to glow, and that's how he knew some particles were formed. The tube glowed when the particles struck it during the experiment. But this is what the setup is. So there are two polarized plates here. There's the cathode plate at the end of the tube, and there's the anode plate close to the edge of the tube. And these two plates or metals were connected to a high electric voltage source. So you have a high electric voltage source, in layman's language, connected to a battery. Okay, now the connection of the setup to a battery seemed to create high moving electrons, high speed moving electrons, and those electrons seemed to move or originate from the cathode and traveled to the anode. That's why this is called the cathode ray tube. Now, the cathode is negatively charged, the anode is positively charged. You know that opposite charged particles attract. So if the electrons originated on the cathode and they attracted to the anode, which is positive, what is your conclusion? The conclusion is that these particles must be negative because they are attracted to the positive end of the setup. Now, how did he know that there's a cathode ray produced, given that you cannot see them with your eye? Remember what I told you before. The cathode ray tube wall in the inside is coated with zinc sulfide, or let's say a fluorescent chemical, which glows when electrons hits it or collides with it. So he observed a stream and glow movement of a ray. Later on, he called that ray, stream of ray, electrons, and we are going there. So now on the cathode, there's a hole, there's a pinhole. As these first high-speed moving particles moved towards the anode, they went through the pinhole of the anode, and then he did some experiment variations. So the first one was the magnet. Let's call this variable 1. The variable 1, we're going to call it the magnet. Ignore anything else you see on here, like the negative here and the positive there. Ignore that for now. So variable 1, the magnet. He introduced the magnet, and he observed that the introduction of the magnet caused the ray to deflect either upwards or downwards. Let's say so. So this deflection, it can go up or down depending on the polarity of the magnet. So what you're just saying is introduction of a magnet caused a deflection of the stream of ray that was produced from the cathode. So the conclusion number 1 for that is that the particles produced from the cathode terminal were magnetically active. So electrons are magnetically active. So that is conclusion number 1, that electrons are magnetically active. Okay, now I know so far he probably doesn't know those are electrons, but he's just saying the particles are magnetically active. But now later on he knew those were electrons. We are coming there. So variation number 2 is gonna be the electric field. So number 1 was the magnet that introduced the magnetic field. So variation number 2 will be the electric field. Let me highlight it. Remove the magnet. Now we're introducing the electric field. We are done with the magnetic field. So the electric field is where you're introducing a negative side and a positively charged side of plates. So this is the negative side of the electric field. This is the positive side of the electric field. Probably they two are connected to a battery. Okay, so he observed that the stream of the ray went away from the negative side towards the positive side. Okay, remember this down here is the positive side. So if the ray is deflecting to the positive side, what do you conclude about the composition of the ray? So that will conclude that the ray contains negatively charged particles. So those negatively charged particles are then concluded to be called electrons, because electrons are negatively charged. We know that now. You see the ray deflected towards the positive side. Opposite charges attract. So the electric field, variable 2, adjustment 2 of the experiment, showed that the ray went towards the positive side of the electric field. So these particles generated from the cathode ray tube are negatively charged, and they are electrons. Okay, now when he put them together, now put variable 1, the magnetic field, and variable 2, electric field, and adjust them in such a way their strengths are similar. Then it was observed that this cathode ray, which is now variable 3, you have both 1 and 2, electric field and magnetic field present, and adjusted in such a way the electric fields or their fields, their effect is even. The ray was observed to go through to point B. Okay, so that tells you that these electrons are charged. Okay, they are charged. So this was the cathode ray experiment that was done by Thompson. So in conclusions, electrons were made from the cathode side of the tube, and the ray traveled through the anode And when you introduce the magnetic field, the ray was deviated probably upwards. Now if you switch the polarity, it will deviate downwards. So the ray contains particles that were magnetically active. Now if you remove the magnetic field and introduce electric field with the negative and positive side, the ray deviated to the positive, and that tells you that those particles were negatively charged. Okay, and that concludes that those particles were the now known particles we call electrons. Electrons are negatively charged particles. Now if you bring both electric field and magnetic field and balance their strength, the ray will pass through in the green line. Okay, they'll pass through with the green line, and they will pass through, the ray passes through undeviated, not up, not down, not left, not right, just through straight. Okay, so in conclusion, Thompson helped to discover the existence of electrons, and also that the electrons are negatively charged. But did he tell us the numerical value of this charge of an electron? No. Someone else did that. We are going to discuss that next. Later on from this discovery, Thomson discovered a number, which is the mass to charge ratio, or let's say the charge to mass ratio. The ratio of the charge of an electron to its mass, E over m, he found it to be 1.7588 times 10 to the power 11 coulombs per kg. Through this, he won the Nobel Prize in 1906. Now, he did not tell us the charge of an electron. He did not tell us the mass of an electron. The oil drop Millikan's experiment did, which we'll discuss next. By the way, this experiment was done in vacuum conditions in the cathode ray tube. So, since Thomson only discovered the charge E minus to the mass ratio and never gave us the charge itself and the mass itself, Millikan, the scientist, came up with the Millikan's experiment to determine both the charge and mass of an electron. Isn't that cool? Now his experiment is very much complicated. We will not go into the scary calculations that he followed, but I'll just give you a general idea. So between 1906 and 1914, he designed this experiment and adjusted the parameters and found that Millikan found that the charge value of an electron is negative 1.60 times 10 to the power 19 coulombs. How did he do it? So he used an atomizer. Think of this as a mist creator of particles, so where he is pumping here to form a mist of oil, and then those oil drops, the mist of oil drops, they find their way down a charged plate. This plate right here is electrically charged, is positively charged, and this one is negatively charged. So there's a pinhole in there in the top plate, what you would technically call the anode, that allows maybe just one oil drop at a time from the mist of the oil to pass through like that, to pass through. Now as the oil drop down here, there is a source of X-ray. The source of X-ray, what it does, it shines X-ray into the sample of drops that is coming down in the air. So imagine the X-ray charging the air particles in this area, and then the air particles that are charged collide with the oil drops, and the oil drops themselves now become charged somehow. They become charged somehow, you know. So and once the oil drops are charged, he will be observing through a microscope here to see how fast they are dropping down. So because that one will help him to find the mass of an electron based on the mass of the oil drop. So there are different forces acting on these oil drops. One is gravitation force that is forcing the oil drops to go down, then the electrostatic force, and then there's the viscous drag force. All these parameters he used in his calculations, which we are not going to go into. So through a micromirror eyepiece of a telescope, he would observe the oil drops going down. Okay, remember those oil drops are colliding with air particles, or if you want, air molecules in the air that have been charged by the X-ray, and then those charged particles in air or molecules, they would in turn charge the oil drops. Okay, and then these oil drops will be falling down as he observes them through the microscope. The rate of dropping of the oils can be adjusted by increasing or decreasing the electric field strength. With this experiment, he observed that the magnitude of charge Q is always a multiple of the electron charge E. So there could be a factor of n here, where n is 1, 2, 3, 4, 5, 6, 7. So Q, the amount of charge on the oil drops, was always a factor of E. Using the charge of the electron and Thompson's charge to mass ratio of negative 1.76 times 10 to the power 8, the mass of an electron could be determined. So he did a lot of calculations and adjusted his parameters to find this number. So he was successful to find the charge of an electron and the mass of an electron to be 9.1 times 10 to the power negative 28. So this is quite a very summarized process of this setup of Millikan's experiment, but that's all he was going for. And in summary, that is the setup as shown on this slide. So yeah, Millikan helped us using the oil drop experiment to determine the charge of an electron, which Thompson could not. Thompson only found out the charge to mass of electron ratio. So Millikan's found out that the charge of the electron is negative. Yeah, the electrons are negatively charged, negative 1.6 times 10 to the power minus 19 coulombs. Okay, and then he also found by calculations that the mass of a single electron is 9.10 times 10 to the power minus 28 grams. An electron is almost weightless, massless. It's very, very light compared to proton and neutrons, which is why we don't use electrons in calculating the mass of an atom of an element. They are very, very light compared to the protons and neutrons. So now we can use the charge and the mass to prove Thompson number to be right, and to show that Millikan's experiment correlated or agreed with Thompson's value of charge to mass ratio of an electron, okay, from the cathode ray tube. So let's do that. Let's find the charge to mass ratio of an electron using the values from Millikan's oil drop experiment. So we have negative 1.60 times 10 to the power negative 19 coulombs. Divide that charge by the mass of an electron, which is 9.0 times 10 to the power negative 28 grams. Let's see if our answer will be negative 1.76 times 10 to the power 8, to prove that the two experiments, Millikan's oil drop experiment and Thompson cathode ray tube experiment, that they correlate. they agree with each other. So I will take my 1.6 on my calculator here, make it an exponent of negative 19, and then I'm going to divide that by 9.1 exponent negative 28, and the answer, yes, you can see the answer is negative 175,824,175. That is like 178 million, but with the negative value. That's gonna give us 8 zeros. So the answer here is negative 175,824,175. I think we can stop there for now, and then we can write this in scientific notation. It's quite a big number, so we are going 1, 2, 3, 4, 5, 6, 7, 8. So this can be written as negative 1.7 in 3 significant figures. I see I have an 8 after the 5, so the 5 becomes a 6. Negative 1.76 times 10 to the power 8. The unit is coulomb per gram. And that proves to us that the charge to mass ratio correlates. So he got the right charge and the right mass from his multiple runs of this experiment and some tough calculations. This is just a summary.